I don't know. Patrick, can you hear me now?
Yes,
I
sir. I hear
can't
you
hear
now.
you because it's randomly pairing to my Star Wars speaker in my office upstairs. Let's
Weird.
see.
I hear you now. Can you hear me?
I can now hear you that I turned it off of. You were talking to my speaker through my speaker upstairs, probably scaring the shit out of passersby. Sorry about that.
All good.
Okay. Sorry, I don't know why it just decided for the first time ever, because I don't even remember pairing my Bluetooth speaker to this computer. But anyway, um, so hopefully this will be fixed from here on out. Hide meeting controls. Okay, so there's our mathematical equation for electron drift. And for what it's worth, this equation is literally just Ohm's law if you're a physicist, where that Q and mu is conductivity, like we described in class on Wednesday, where there's no hole contribution here because this is a metal and we just have electrons as charge carriers. Okay. So we'll get to what's going to happen in a semiconductor in a moment, but it's just going to have a second term taking into account holes. So the last two variables in this equation represent the drift velocity of the carrier. So let me just denote that. So this expression right here is what's typically called the drift velocity, where the drift velocity is the average velocity attained by a charge carrier due to an electric field. Where I can say that there's going to be some electron drift velocity, V sub E, that is going to be negative mu n times E. And this negative sign is simply indicating that electrons are going to move opposite the direction of the applied electric field. So if the E field is oriented from left to right, the electrons are going to move from right to left. And then we're going to have some hole velocity VH that will just be, I used mu sub P times E. So holes move in the same direction of the electric field. So putting these things together for a semiconductor, we would have a total drift current density, J drift total, would be the drift current driven by electrons plus the drift current caused by holes, or negative Q n mu n E plus Q P mu P E, taking out the Q and the E. And actually, I'm going to put a sub E there and a sub P here. So negative times the charge of an electron, which is also negative, that's going to get rid of that sign. And so I'm just going to have the fundamental charge 1.602 times 10 to the negative 18 coulombs times n mu n plus p mu p e, and this guy right here, or actually this part right here, including the q, is just the conductivity that we talked about in class on Wednesday. Okay. The other mechanism is diffusion. Okay. So carrier diffusion occurs when there are variations in the carrier concentration across a medium. So I'm going to use a bit of a vulgar example here because it's my favorite kind of example. So sorry, Hannah. Um, if I were to fart in this chair, okay, there would be a concentration of, let's say, poop particles, because I can't think of a better word than that. And they would largely start concentrated in this area. So there would be a high concentration of poop particles where I'm sitting and a low concentration of poop particles in the remainder of the room, okay? But over time, those poop particles would diffuse so that everyone would smell it, not just he who dealt it, okay? So that is the diffusion's mechanism, all right? So we need a concentration gradient or a place where there is a very high concentration of charge carriers and a very low concentration of charge carriers that they're going to flow towards. So whenever a concentration gradient occurs, charge carriers tend to flow from a region of high concentration to a region of low concentration due to repulsive Coulombic interactions between the carriers. This movement is governed by what's called Fick's law, where we're going to have J diffusion is going to be our fundamental charge Q times our diffusion coefficient for our electrons times the spatial derivative of our electron concentration, where we're just doing things in the x direction here, but obviously we would have a y and a z, potentially a y and a z gradient as well, minus our whole diffusion coefficient times the derivative of our hole concentration with respect to position as well. So I'm just going to make a quick note here. This is the electron diffusion coefficient having units of centimeters squared per seconds, and d subscript p is the hole diffusion coefficient. And it also has the exact same units. Now, while drift and diffusion occur for very different reasons, the coefficients which quantify their effects are related to each other by what's called the Einstein relationship, okay? So let me just try to sneak this in here. So the Einstein relationship goes as follows. The diffusion coefficient, and I'll just do it for both, even though it's the same relationship, divided by the mobility is equal to Boltzmann's constant times temperature, or our thermal voltage, over charge. So this is the one for electrons. And then very similarly, we'll have d sub p over mu sub p is equal to kBT over Q for holes as well. So if you only know the mobility, but you know temperature, you can figure out what diffusion coefficient is, and vice versa. If you only know diffusion coefficient and you know temperature, you can figure out what mobility is going to be. All right, so this is the end of the electrical review. And so now I would like to start talking about noise in MEMS systems. So in an electrical system, noise is attributed to the random motion of electrons found in a conducting medium. Similarly, in a mechanical system, noise is attributed to the random thermal vibrations of atoms in a mass. So what we can see from both of these definitions is that noise is a random process, okay? So since noise is a random process, the value of noise cannot be predicted. At any time, even if past values are known. So as a quick example, I'm going to attempt to draw two crappy graphs here. Right? So our first will be a simple sinusoidal signal, where we have time on this axis and our waveform on this axis. And here is my shitty sinusoid. So if I were able to draw well, we should be able to see that this signal is going to repeat itself at regular intervals. So this is a periodic function. Um, where we are able to predict values of f of t for times greater than its period, assuming that this point right here is 0, because we know the prior values of the function. And then down here, I will attempt to scribble a noisy function. So here's time, and let's call this guy just g of t, so it's denoted by something else, and that might be something like this, okay? Where this is an example of an aperiodic waveform with no discernible pattern. So, excuse me, values of g of t cannot be predicted. And I put a little asterisk there, which is what we're about to talk about. Okay? Um, so if noise is a random process, how can we do any kind of analysis that tries to take it into account? Okay. So the instantaneous amplitude of the noise can't be predicted, but the average power typically can, because usually noise is going to fall into a well-behaved probability distribution, right? So essentially, by observing noise for a long time, we can often develop statistical models that let us know a range of, I'm going to put in quotes here, expected values. So let's look at a resistor. Okay, so the average power delivered to a resistor by a periodic voltage, like our sinusoid above, is given by the relationship P average will be equal to 1 over the period of the waveform that we're applying across the resistor. We're going to integrate over one period, which I'm just going to choose to represent as from 0 to t of the voltage drop across our resistor, which is our function f of t. I'm going to square it, and I'm going to divide it by my resistor value. And I'm going to integrate this with respect to time, right? So if we've got a periodic AC waveform, we have V squared over R, which is the power. We integrate it over one period and divide by the length of that period, and we get our average power. Okay. For a non-periodic voltage, like G of t, this measurement must be carried out over a longer period of time. So we're going to have something like this. It's going to be roughly the same relationship, except that I'm going to take the limit as I allow my period to approach infinity. We are going to define our noise voltage seen by the resistor, Vn squared, is going to be our average power divided by our resistor value, which will simply be the limit as t approaches infinity of the integral from 0 to t of our voltage waveform squared. So for most physical noise sources, the instantaneous amplitude of the noise will follow a Gaussian distribution. Meaning that approximately 68% of all noise amplitudes will fall within one standard deviation. Okay. And on the flip side of that, that means that the chance of us seeing a noise larger than 3 standard deviations is about 0.3%. Okay, so we're going to have a pretty well-defined range of what we should see, although we won't be able to say, well, the value is going to be this. We know it's most likely going to be between 2 discrete points. Okay. The standard deviation of the average noise voltage is the RMS noise voltage oops, excuse me. Goodness gracious, my penmanship's getting really shitty. Defined as VRMS will be the square root of the square, the square root of our noise voltage, I guess, since we defined noise voltage as Vn quantity squared. This is a thing that always kind of tickles me or whatever. So we're using this noise voltage as an analog for power, right? Because if power is V squared over R, but the size of the resistance is arbitrary, right? It's going to be proportional to V squared. So that's what we're calling our noise voltage, but we're really using that to represent power. Our standard deviation is just the square root of that quantity. Okay. So noise sources can be correlated, goodness gracious, or uncorrelated. So let's talk about this really quickly with a simple example. Okay. Let's say we go to a football game, not in the Joe because we want people to be there and there to be actual noise. Okay. So let's say we go to a football game at the Superdome or something like that. Okay. So when you're sitting at the game, there's going to be people having conversations, this, that, and the other. You might hear people, talking to each other, shouting at folks, drinking beers, all of that kind of good stuff. So those are examples of uncorrelated noise, okay? However, let's say the Saints score a touchdown, which this season would be, a huge deal. You'll hear a lot of people shout, scream, hoot, and holler at the same time. That is a correlated noise because it's occurring due to the same event, okay? So that's really the difference between uncorrelated noise and correlated noise. Uncorrelated noise means that they are not caused by the same thing. Correlated noises are caused by the same event. Okay? So when two noise sources produce uncorrelated noises, VRMS1 and VRMS2, and we can very easily generalize this in a moment, okay? The total RMS noise will be the sum of the squares. And then we take the square root of that sum, okay? So for my electrical engineering folks, you may or may not remember this, but this is literally how we add RMS values for sinusoidal excitation at multiple frequencies, where each individual excitation source isn't related to the other one, right? So if I'm exciting a system at 120 hertz and 240 hertz, you would add the results together to be able to do your power analysis and all that kind of stuff. Covered it in circuits 2 forever ago for you guys, but you have technically seen this before, okay? If the noise sources produce correlated noise, the total RMS noise will be VRMS total is simply the sum of VRMS1 and VRMS2. We got okay. So now let's talk a little bit about noise in the frequency domain. Which means we're going to talk about noise spectra. So to put this in context, let's talk about people talking again. Okay? So if you listen to a group of men speaking, generally, if you looked at the spectra of the noise that they are creating, it's going to be at a lower frequency than that of a group of women talking to each other because men's voices are typically deeper, right? That's all that is, okay? So if we looked at a spectrum analyzer, we would actually see when we looked at what frequencies things are happening at, noise generated by men is going to be appreciably different than the noise generated by a woman. That's typically quantified by what's called a power spectral density. So power spectral density, why did this switch over to be straight lines? So this is going to have a symbol of Vn squared with a bar over it. So again, for those of you that are EE inclined, we're using bars over numbers to represent complex numbers because we're in the frequency domain again, just like we've done in all of our other classes. And this power spectral density will have units of volts squared per hertz. Okay. Where again, volt squared is proportional to power for an arbitrary resistance. And then because we're dealing with voltage as a function of frequency, we need that hertz in there as well. Okay. So power spectral density is defined as the average power carried by a signal in a 1 hertz bandwidth around a specific frequency. Okay. And we're also going to have what we call just our regular spectral density, which is going to be Vn with a bar over it, measured in volts per square root of hertz. Is simply literally the square root of the power spectral density. So in the frequency domain, the RMS noise voltage is defined as VRMS is the square root of the integral of our power spectral density as a function of frequency integrated across all frequencies. So the two most common types of power spectral densities that we might see are white noise and 1 over F noise. So white noise is a power spectral density, excuse me, that is constant across all frequencies, meaning that Vn of f just has some single value, right? Graphically, we might see something like this. So on The y-axis is going to be our power spectral density. So I'm just going to write that out as PSD. And over here is going to be frequency. So I'm going to draw a line here representing essentially the peak value, and I'm going to try to kind of color that in, meaning that everywhere under that line is an acceptable amount of noise that would quantify under that. Okay? Because real systems have a finite bandwidth, the measured noise will be shaped by the measurement system. Where our measured noise might be something like this. So our power spectral density of our system is going to be the magnitude of our system's transfer function squared. So let me just make a note of that. Yep. Shaped times our power spectral density. So to try to show you what I'm throwing here, if we had a system characterized as generating white noise, and then we put this through a low pass filter. So here's our noise spectral density, or excuse me, power spectral density. Here's the square of our transfer function, which this is just going to be a simple single pole low pass filter. So its transfer function might look something like this. The measured noise would just be the product of those two waveforms. Which might look something like this. The RMS value of white noise is given by following relationship. So we'll say VRMS is going to be the square root of that measured noise equation we have above. So HF squared times our power spectral density integrated with respect to frequency. And since for white noise, our power spectral density, or the square root of our power spectral density, is a constant, we're just going to pull that guy to the outside. So we would have Vn times the square root of the integral of simply our system's transfer function squared, integrated with respect to frequency. And the bandwidth of our noise will be given by the expression bandwidth is equal to 1 over the square of the peak value of the transfer function times the integral of our transfer function squared integrated with respect to frequency. The most common form of white noise is thermal noise. However, technically that isn't even really white noise, because at frequencies greater than about 80 terahertz, it starts to actually have a non-constant value. Luckily for us, that's way higher than most measurement systems can ever actually deal with. So we just treat it constantly as white noise. The other noise spectral density or power spectral density that I want to talk about is 1 over F noise. Okay. So as the name implies, 1 over F noise is inversely proportional to frequency. That's what the 1 over F is for. Okay. 1 over F noise happens a lot in semiconductor materials, explicitly semiconductor materials that have an oxide layer grown on top of them. So in transistors, this is going to happen a whole hell of a lot. We'll also see it in piezo resistors and things like that. Okay. So 1 over F noise happens because of the random trapping and releasing of charge carriers in an electrical component. So the reason why it happens so often in semiconductors with an oxide layer is, I'm going to draw an even shittier picture than normal here, so bear with me, okay? So let's say that we have something like this, okay? So this line right here is representing a material interface, okay? So up above here is our silicon dioxide, and below here is just our silicon, right? So down here in the silicon space, we have extremely well-ordered periodicity, all of that kind of good stuff, right? Except that at that material interface, we have, from the standpoint of crystallography, a defect. The defect being the crystal ended. So if we wanted to have technically a perfectly pure crystal from a crystallographic standpoint, it needs to be no defects anywhere ever. This guy has a defect because it stops being a crystal at that boundary, okay? So everywhere inside of the bulk of the crystal, we have those electrons that are covalently bonded to each other. Everything is behaving really well. Well, up above here, I'm just going to draw some scribbles in gray. This represents amorphous silicon dioxide, right? Silicon dioxide, unless it's grown specifically to be quartz crystal, isn't going to have any periodicity or anything like that. So we have broken covalent bonds that are constantly looking for another electron to fill them up. So those broken covalent bonds at that material interface tend to trap free electrons when it can find them and hold on to them And that's what's causing the 1 over F or the flicker noise, is it grabbing those electrons and then just randomly releasing them whenever they get enough thermal energy to escape that trap. Okay. So our 1 over F noise spectral density, V 1 over F squared with a bar over it, is going to be defined as, sorry, my wife is flirting with me. I shouldn't have said that out loud. This is recorded. She'll never watch the video, but anyway. Goodness, I got distracted. Actually, sorry, there shouldn't be a square symbol right there. My apologies. It's going to be our power spectral density multiplied by what's called the ratio of our corner frequency over our frequency of interest. And I'm going to put where F sub C is the frequency at which the 1 over F noise and white noise have the same amplitudes. So graphically, that would look something like this. Okay. So power spectral density on this axis, frequency on this axis, and I'm specifically going to say that this is in log scale so I can just use straight lines. So our white noise spectral density, like we talked about earlier, is constant across all frequencies. So fill that in. Our 1 over F noise, let's do that in blue, might be something like this profile, right? So as frequency increases, our 1 over F noise goes down. And then this point right here is our corner frequency. So this line is 10 log V1 over F squared. And this line right here is just 10 log our white noise power spectral density. Okay. The RMS noise due to 1 over F noise is given by the relationship VRMS will be equal to the square root of the integral from our lowest frequency of interest, FL, to our highest frequency of interest, FH, power spectral density, FC over F, dF, or the square root of Vn squared times our corner frequency times the natural log of FH over FL. All right, I'm almost done ranting at you guys. What time does this class end? Um, actually, I still have three. Let's call it here. My hand's getting tired. I'm sure you guys are tired of my bullshit. And I've got 3 more pages of notes, so let's call it here.